Hello. We're going to learn what similar polygons are today. They're not that much different from what you might expect from the name. If you know what similar means, I'm sure you do. First thing you should understand about similar polygons is that the angles inside are going to be congruent. In other words, if this polygon, this rectangle, is similar to this polygon, corresponding angles have to be congruent. This angle is congruent to this angle, this one to this one, and on down the line. Now, I drew these as rectangles, so I can just tell you right up front, these are all 90-degree angles, and these are all 90-degree angles. So, does that mean every rectangle is similar to every other rectangle? No, not at all. For instance, this over here, this is not similar to these two. These two are similar to each other. Why? You can probably see that there's something similar about the way they look. They have something in common. What is it? Well, what they have in common is the ratio of, suppose I put a label on this, we'll call this A and this A prime, and this will be B, and this will be B prime. Well, these two aren't the same, but the ratio of A to A prime equals the ratio of B to B prime. See what we're doing here? For instance, if this side were exactly twice what this side is, then this side would have to be exactly twice what this one is. Otherwise, they won't be similar. So, I think you're getting the idea that what we're really talking about here is objects which have retained their shape, but not their size. The ratio of length to width here is the same as the ratio of length to width here. For instance, suppose we had a square. Well, this is almost like a square over here. Now, every square is going to be similar to every other square. Why? Well, let's try it. Let's just make ourselves another square down here. I'm not sure if either one of these are perfect squares, but we're going to say that they're squares. So this has side, let's say it has length L. Well, then this has side length L also, and it's the same all the way around. That's what it means to be a square. Well, that means if I shrink this one down to some fraction of L, say this is L over 2, well, it's still a square. Well, that means this has to be L over 2. They all have to be L over 2. That means that the ratio of this side to this side is exactly the same as the ratio of this side to this side. Remember, you can say it either way. Over here I use the ratio of the small one to the big one. Here I use the ratio of the larger one to the smaller one. You can do it either way. Just stay consistent is all within any particular pair of polygons that you're investigating. For instance, don't write compare the ratio of this side to this side and then the ratio of this to this. You got to maintain the order, otherwise you get L over 2 and then L over 2 over L, and those aren't going to turn out to be the same. You have to put the big side over the small side here, then you put the big side over the small side here. If it's the small side to the big side, then it's the small side to the big side. Seems obvious, but it's easy to mess that up. Down here, these are all the same triangle. I just changed the size. And I changed all the sides the same way. So that, in fact, no. Now the angles, I pulled these in here. These are all 90-degree angles, so I didn't actually write them in. These are not 90 degrees, and you can't make any assumptions about, I should have put it in there too, shouldn't I? You can't make any assumptions about these. They kind of look, if they look equilateral or isosceles, They're not intended to be any particular type of triangle. They're just similar. And why? Well, because the angles are congruent, and all three of these are similar. The sides have the same ratio. How do you know that? Well, you don't have any way of knowing that other than I just told you. You can look at it and see that that's true. I use the expansion and contraction tool to produce these, so I know that they're similar because the software did it for me. I didn't have to eyeball anything. And other than me telling you that they're similar, there's no way you could know at this point. We will have some theorems later on that will allow us to prove that two polygons are similar. But right now we're just learning what the heck similar polygons are, so it stands to reason we don't have any proofs yet. Well, I said we don't have any proofs. I should have said we don't have any theorems yet. Pardon me. If you're looking for real-world examples of similarity, you can start with scale models. That's a perfect example because they are, by definition, similar. If they're true scale. For instance, they make some really nice train sets that are models of real engines. They're very detailed, and they're done to scale, which means that the proportions are the same all the way around. If the height of the model engine is, say, 1/1000th of the height of the real engine, then the length would also be 1/1000th. If it's a model of an old steam engine, the smokestack would actually be exactly 1/1000th of the original smokestack. And all the way through, every single thing which could be measured would be 1/1000th of the original. That makes it similar. Although, obviously, a train engine is not a polygon. We're going to be working with things that are much simpler than things like electric trains. But that is the idea. The perfect example of a real-world similarity is scale models. And by the way, what I just said about model trains, if each piece in the model is exactly 1/1000th of the original, then that number 1/1000th, that's called the scale factor. If you hear that term scale factor, that's exactly what they're talking about. It's the factor which scales it up or down. In the case of the electric trains I was talking about, the model trains, your scale factor would be 1/1000th. I don't know if that's actually a legitimate scale factor or not. Probably not. I just pulled that out of a hat. And speaking of scale factors, there's a special case that we studied earlier called congruence. Well, that corresponds to a similarity with a scale factor of 1. That is the ratio of one side of, say, a congruent triangle to another side of the other congruent triangle. It's just 1 to 1. The similarity and congruence are related. They're not the same thing, of course, but they have a relationship. And as we work problems, it will become much more obvious. Here we have two similar polygons. How do you know they're similar? Because I just told you. If I hadn't told you that, there'd be no way you could actually know for sure that they were similar. They look like they could be, but until you have more information, you just have to be told whether they're similar or not. What is the scale factor here? Well, that's something. I'll use the actual scale factor for what we're going to do, but the result is going to be true no matter what the scale factor was. A prime here equals 3/2 of A. That's the scale factor. So, what's the perimeter here? Well, just A plus B plus C plus D. If we write out what our perimeters are, these two similar polygons. And remember, the perimeter is just the sum of the sides all the way around. In other words, the distance all the way around here, following the straight sides, of course. And that's just A plus B plus C plus D. That's P1. Now the perimeter here, of course, is all the way around the sum of all the primes, A prime, B prime, etc. But there's a relationship because they're similar. And this ratio has to hold all the way through. If it doesn't, they're not similar. The fact that one side is proportional, this side here on this polygon is proportional to this side on this polygon. The fact that these two sides are proportional, that's not enough to produce similarity. Every side has to be proportional, and it has to be the same proportion. So it has to be that B prime is 3/2 of B, and this 3/2 of C, and this of course has to be 3/2 of the original D. This has to hold all the way through. It's related to the scale factor. In fact, you could call it a scale factor. In this case, it is 3/2. That's going from the small one to the big one, of course. So, if we substitute those expressions in here, now we have our distributive law, which allows us to pull the 3/2 out from each expression here and write 3/2 A plus B plus C plus D. But this here, this is just P1, isn't it? So we have 3/2 P1, and that's what P2 is. So the perimeter of this one is 3/2 the perimeter of this. If this perimeter was P1, here we have P2. Well, it turns out P2 is 3/2 of P1. In other words, we could write it this way. The ratio of the two perimeters is exactly the same as the scale factor, or the ratio of the sides. The perimeter got scaled down exactly the same way the sides did. That's probably what you expected, but now you know. What you expected is exactly right. All this stuff will be much clearer as we work some problems and demonstrate the stuff we were talking about. We got the triangles ABC and DEF are similar. I went ahead and sketched them in down here, and I drew them so that they in fact are similar, just so that the visuals match up what they're saying. What do we have here? Which statement is not correct? Okay. Remember, if they're similar, that means the corresponding sides are all in the same ratio. So AB over DE would have to equal BC over EF. And in fact, BC over EF, okay, that's one. Huh? It says BC over EF equals BC over EF. Well, jeepers. That's always true. It really doesn't matter whether you've got similarity or not similarity. What they're saying is that the ratio of this over this is equal to the ratio of this over this. It's just like saying A equals A. And this is just the reflexive property. It has nothing to do with similarity or triangles or anything other than equality, which says that things are equal to themselves. So, assuming this isn't a misprint, it's certainly true. How about this one? AB over DE. Let's see here. We got AB here and DE here. So those are corresponding sides. CA. There we go. And FD. And those are corresponding sides. So we have the ratio of this side to this side is equal to the ratio. Wait a minute. Yeah, that's right. No, it's not right. Doggone it. I never should have drawn the picture. All I'm doing is confusing myself. AB over DE. That part makes sense. Okay. CA over FD. Right. Since they're similar, those ratios have to be the same. The ratio of this to this has to be the same as the ratio of this to this. Okay. What about CA over FD? Should have come up with simpler names for these sides. Here's CA and FD, of course, so that makes sense. BC over EF. Well, that makes sense too. What about this last one? AB over EF. That's this. Wait a minute. AB over EF. AB and DE are the corresponding sides, not EF. And then BC and DE, well, no, BC and EF are the corresponding sides, and then AB and DE. So this one doesn't really make sense because the side that corresponds to this side is this one, not this one. Just like with congruence, corresponding parts of congruent triangles are congruent. Well, corresponding parts of similar triangles are in the same ratio. But if they're not corresponding parts, you can't say anything about the ratio. Now there's another one of those error analysis problems. Somebody came up with a perimeter of 56 for B. Well, what's the perimeter for A? Well, we get 10 and 6 is 16, and 12 is 28. Okay. Well, what's the scale factor here? I think we're told that they're yes, we know that they're similar. If we weren't told this, there's no way we could know. But we're told that they are similar. And we're only given the dimensions of one side here. But since they're similar, they have to hold all the way through. And 5 is pretty obviously 1/2 of 10. So the scale factor is 1/2 or 2, depending on which direction you're going. Since we have the perimeter for A, I guess we could say the scale factor from A to B is 1/2, which means the perimeter of B is 1/2 of 28 or 14. How did they get 56? Well, 2 times 28 is 56. So they just forgot the difference between 2 and 1/2, I guess. No, they just got the scale factors mixed up. You see, if you're going to the small one, it's 1/2. If you're going that way, then it's 2. But we're going down, so you should have used a scale factor of 1/2. That's all you have to do is just cut the perimeter in half, and you've got the new perimeter. Here we have one where we're going to demonstrate what we just did in a previous problem. The scale factor from figure A to B, well, maybe I should have labeled it. Here's figure A, and here's figure B, is 1 to x. That's the scale factor. Now in this case, the scale factor is, I think, 4/3. What about going from B to A? So if we go this way, what's our scale factor? You just have to reverse it, that's all. For instance, in this case, it was 1 to 4/3, I think. Okay. Well, if we write 4/3 to 1 here, remember these can also be interpreted as fractions. So if you write the scale factor as a fraction, I think it's easier. For instance, this is 1 to 4/3. Yeah, that's the same as 3/4, really. 1 over 4/3. So this is 3/4 of this one. Or going the other way, it's 4/3 to 1, which is 4/3 over 1. So you could say this is 4/3 of this one, or this is 3/4 of this one. So as you go the other way, you just take the reciprocal. So whatever your scale factor is from A to B, if that's the scale factor is k, then going the other way from B to A, your scale factor is just 1 over k. Just the reciprocal. It's probably what you would expect. Since you go this way, you expand or contract by k, and if you go back the other way from B to A, you just reverse it. You multiply through by 1 over k, and that just puts you back where you started. So you go this way, you use your scale factor of k, you go the other way, use your scale factor of 1 over k, and your A will be right back where you started, which is of course what you want. Now in this problem, we're given that these two triangles, here and here, are similar. And we've got, they labeled this side and this side, so we can compute the scale factor or similarity ratio. Now they're asking you about this here. What about these lines? We know that the angles are all congruent because they're similar. We know that the sides all have the same proportion because they're similar. But what about this? Well, this is the perpendicular distance from the vertex to the opposite side. And so is this. We have a name for that, don't we? It's called an altitude. Well, it turns out, and we can prove this once we've got a couple of simple theorems under our belt, we can easily prove that all the parts that we have defined in a triangle have the same similarity ratio. The altitudes, mid-segments, the mid-segment of this would be in the same proportion as the mid-segment of this. For instance, this is 18 over 27, right? That's 2 over 3, 2/3. So the ratio of this to this is 3 to 2. Then this has to be 3 to 2. The mid-segment has to be 3 to 2. The meridian, the perpendicular bisectors, all of them will be in the same ratios. And it'll be easy to prove that in the next section, which seems odd to me that we would work these problems, but they're in the book, so I thought I'd go ahead and do it. It seems to me I would leave a problem like this until after we proved that these two altitudes had the same similarity ratio. But for now, we're going to accept it as a fact, and we'll prove it in 1 or 2 sections. For now, accept the fact that all the parts of similar triangles are also similar. The altitudes, the mid-segments, the medians, etc. Which makes this pretty easy. All we have to write is, once you know that little fact that they all have the same ratio, then this is pretty easy. Because we got 27 over 18 must be the same ratio as x over 16. Real easy. So then we can easily set up our equation. We get 27 times 16 equals 18x. And of course we divide it through by 18 and we get our 27 times 16 over 18 is the value of x. We do little cancellations and get that x equals 24. Pretty simple. The hard part of this is knowing that all the components of similar triangles are also in the same ratio. Well, here we're given some information about two similar triangles. I went ahead and drew it in here. So we got a picture of what we're working with. Chances are you could do this just purely with algebra, but let's not. Now they gave us an altitude, which we're not going to need, but we will need some of this information. For instance, they had to give us at least one side, and they say that the short side is 8 inches, and if they're similar, I drew them so that they had the same orientation. Here's the short side here, so this is the short side. What does that look like in terms of a ratio? Well, it looks like this is 8 to 6, or 8/6, which would be the same as 4/3. So, going from here to here, we have to multiply by 4/3. In other words, 8, this side right here, is 8 times 4/3. That's your scale factor there. Here, 10 times 4/3. And that one's about 13.3, I think. I'm gonna have to, I'll check that with the calculator. And if we do the arithmetic, we should get that ST is 10 2/3, that's 8 times 4/3, and RT is 13 1/3. If you got decimals, that works too, 10.66 and 13.33. All you had to do was figure out your scale factor from the knowledge of these two sides, and then you can compute the other two. That's pretty easy. Here's one that's pretty simple. You just need to understand what it means to be for two polygons to be similar. One of the things that similarity implies is that all the interior angles are congruent. The sides aren't, but the angles are still congruent, just like they would be in congruent objects. In similar polygons, the angles are still congruent. So, we're given the ratio of the angles inside this triangle, and they want to know if you need any more information to figure out the ratio of the angles inside this other similar triangle. And the answer, of course, is no, because the corresponding angles in similar polygons are all congruent. So whatever's true about the angles in one is going to be true about the angles in the other. Pretty simple. You just needed to recognize the definition of similar. Now here's one that's going to combine a couple of things. Going to use what we know about similar triangles, but I have a feeling, well, let's wait and see. Pythagoras' theorem may sneak its way in here. Let's find out. We've got a right triangle with sides of 3 and 4 over here. Now, we have one over here which they say is similar, and the short side over here is 4.5 feet. Now what they want to know is, what's the length of the hypotenuse here? What's this? Well, we could compute this length using our ratio of 4.5 to 3, which is the same as 9 to 6, or 2/3. We could do that. Or, since they're similar, we could compute this hypotenuse and then apply our similarity ratio or scale factor. I think this one's easier because this is a 3, 4, 5 triangle. I know it seems like it's weird to just memorize sets of squares. In other words, a squared plus b squared equals c squared, where a, b, and c are all integers. But the 3, 4, 5 is so common in its multiples that it's not a bad idea to remember that one. It's easy to see. You get 3 squared is 9, 4 squared is 16, 16 and 9 is 25, and the square root of 25 is 5. And the cool thing about this is it holds in multiples also. For instance, you could write 6, 8, and 10. In other words, double every single one, and it would still hold. If you don't think so, square it and add it up and see if it works. It will. You can go 9, 12, 15. And you can go 30, 40, 50. It all works. Well, okay, that's enough of 3, 4, 5. What about this over here? Well, the scale factor we know. Let's do it for real here. 4.5 over 3. Yeah, 4.5 over 3, as I mentioned before, is 3 halves, or 1.5. So if we apply that here, this is 5 times 3 halves, or 7.5. And luckily, that's one of our choices. Now here's a good one to think about. Seems to me it's worth knowing. Do you remember what reflexive, symmetric, and transitive mean? Remember, reflexive, these are frequently, we'll consider these in terms of properties of, say, equality. Remember, reflexive was that A equals A. What was symmetric? That is, if A equals B, then B equals A. Means it goes both ways. And transitive? Well, that was if A equals B and B equals C, then it must be true that A equals C. Well, let's start with a polygon A. Would it be similar to itself? Yes. Why? Well, we already showed that congruent figures are similar. The similarity ratio is just 1. It's 1 to 1. So, and we know that a geometric object is always congruent to itself, and therefore it is also similar to itself. That one's real easy. What about this one? Let's say A is similar to B. Now there's some similarity ratio. We'll call it A to B. Is there a similarity ratio going the other direction for B to A? The answer is yes. We already showed that it was B to A. In other words, the reciprocal. We can write this as A over B, and this we can write as B over A. So we have a similarity relation between the two. They must be similar. And we already showed that this holds. So we've got symmetry. What about transitivity? Well, let's try it. Suppose we have A similar to B. Then we have a similarity ratio of A to B. And if B is similar to C, let's say we have another similarity ratio of B over C. Is A similar to C? Definitely. And the similarity ratio is going to be, as we go from A to B, we multiplied each part of A by A over B to get the corresponding part of B. And then we take that and multiply it by b over c to get the corresponding part of c, which means our scale factor is a over b times b over c, or a over c, and we have that a is similar to c with a similarity ratio of a over c. This is not a really cool two-column rigorous proof, but the fact is similarity is reflexive, symmetric, and transitive, and you could reason this way to convince yourself that that's true. Or you can go nuts and have a really rigorous two-column proof, which isn't what they asked for. And that's about it for now.